I'd like to share my solar air heater project with you. I have two units here at various points in completion mounted on either side of this south-facing window. I know what you're thinking. Why are these things on the front of the house? Shouldn't they be on the roof? Well, I have two reasons for that. One is I've got a bunch of photovoltaic cells on the roof and plan to add more in the future. But the second reason is I live in the high altitude desert of the southwest United States, where the ultraviolet rays from the sun can be very strong and tend to destroy things. Built out of these materials, if this was on the roof, it would have a rough time surviving very many summers here. But here I have it under this eave of the house where the summer sun never hits this device at all, yet the winter sun hits it just fine. Looking at the other unit now, you will see how I've constructed this is I've got air ducts going into two separate chambers. The idea here is air gets sucked into one chamber, then it goes through two layers of black window screen material here, then it travels the full length of the box, goes through this opening, and then travels through another two layers of window screen. By that time, hopefully well-heated air goes into the house. The window screen I had chosen here to use is a black anodized stainless steel. Unfortunately, one of its claims to fame was that you can see through it very well, which is not what we want. I wanted the sun to not go through it very well, and instead absorb heat and heat up our air. Well, I didn't have a lot of choice. Other window screen materials, such as the fiberglass fiber covered with plastic, I did not trust would put up with the weather extremes, and I questioned its heat transference ability. Another window screen material is aluminum, which perhaps would have been a good choice, except I had troubles finding it in black that isn't black due to the fact that they coated it with some sort of plastic that, once again, I didn't trust that it would last very long in temperature extreme conditions. I could be wrong. The other thing I worried about the aluminum is the temperature expansion coefficient of aluminum, in that it would start to sag inside this box and at least look ugly, if not create other problems. So to deal with the issue that I suspect at least half of the sunlight goes straight through two layers of window screen, I decided to paint the aluminum side of this insulating material with high temperature black barbecue paint, so that the light that does go through, which I suspect is about half, would then heat up this surface and further heat up the air inside the box. Finally, I did have some structural challenges with this. Notice how shallow this box is. That is by design, because first off, this section without the glass installed is already over 60 pounds. Then the glass that's going to go in it is going to be another 60 pounds. So that's 120 pounds. So the issue here is this brick wall is a facade on the front of this house, in that it is not structural. The roof is not on top of it, holding it down. It just freestands in front of the walls of the house that really do support the house. So it might not take much for this whole wall to just fall forward and fall down. So I didn't want to provide too much lever arm of weight for it to do that. As you notice, it kind of supports my whole weight, so I'm a lot more than 60 pounds. So hopefully this will work out. In this earlier video, you can see how I anchored this box directly to the brickwork with 10 individual anchor bolts. I use these very cool double expanding anchors that put very even tension on the holes I drill in the brick and prevent it from cracking. The other challenge I had is, these are 4-inch ducts insulated ducts. So by the time you add the insulation area that's on the outside, you're over 6 inches. I had a rough time even getting these out here to the eaves and dumping into this box. Certainly would not be able to do anything any bigger without doing major ripping out ceilings and walls inside the house that I didn't want to do. Hopefully this 4-inch ducts will do the job. So I've purchased a very well engineered blower that seems to be very good at dealing with 4-inch ducts and being efficient. Since this bottom board needs to be very strong, I've got an extra cleat in here. It's both glued plus screwed in with high quality deck screws. I also, since it is not a hardwood, but then I soaked it in a very runny mixture of polyurethane and mineral spirits. The idea here is for the polyurethane to really soak into the wood, and then when it dries, it makes the wood much stronger. The other thing to fit the glass, so I took a router that I constructed this very crude guide for, so it would be consistent. I made a consistent cut all the way around, and I very carefully built this before ordering the glass, which may or may not have been the best way to do it. This side is the only side that actually is not glued, and so I can unscrew some screws and take this side out and then literally just slide the glass in, and in theory it should work. I don't have a sash for the top. The idea here is I slide the glass in and then take a piece of 1x2, route it out and position it for a perfect fit, bolt it in, and then perhaps fill in some material behind that sash 1x2 between it and that cover board that you saw on the other unit. The final thing that I've got here that's not shown because I haven't installed it yet is a strip of silicone window stripping. Silicone because it can handle the high heat, that will minimize the airflow between these two sections until it gets down here where I want it to go. I have not installed the insulating material on this side yet, but yeah, I've used sheets of this insulating material to insulate in this entire box, at least the outside parts, and I've sealed up with a combination of the very messy expanding foam and silicone caulking to try to make this box as airtight as practical. Notice I am not putting insulating material between the two chambers because I don't think it will be worth it. If the little airflow leaks between the two, at least it's not coming in and out of the box. I have no idea if it'll make a difference, but I've also put on the other box that's further complete. I actually angled up some funnel-like structure made out of this insulating material to help funnel the airflow up to the ductwork as compared to just hanging out at the top of this box. Another item that you'll see just hanging here is this 1-wire serial bus temperature sensor. These things are very inexpensive, and they will go to the control system that's going to control this box that I will explain later. Notice I also have this window screen material angled that will be close to being perpendicular to the winter sun. So here they are in their completed state. As you can see, the glass came in, and voila! So as explained earlier, this side was taken off, and this top piece did not exist yet. It gave me some wiggle room for when glass came in. I can't say enough good things about our local O'Malley glass company. They came here with their suction cups and dropped the glass right in. They complimented me on how plumb and true I made it. It fit perfectly. So then I got busy, put the side panel back on, and then cut this little 1x2 strip with groove to fit, nice and snug. A little bit of silicone seal on top of it. So as of this time, I don't have the duct work going into the rooms it needs to go into. They just go up in the attic. But I did a quick check, and on today, these panels are running about between 150 and 160 degrees, sucking lots of hot air out, coming out the vent the other end. So this glass turned out it was a 1/4 inch or 6 millimeter tempered glass. It is not the low lead because that was a lot more expensive. I opted to just go with the regular leaded glass, and as far as I could tell, maybe it would only block about 10 to 15% of the sun. You're looking at about 74 pounds worth of glass here on each panel. Obviously, my structure is holding it as of today.
Installing the flexible ducting was more of a pain than it looks. Here you are looking at the intake and exhaust ducts of one of the panels. As you can see, it gets real tight at the very end. I couldn't even get my body back there, and so had to pull the ducting in with a pull wire. At the very end, I even had to squish the ducting into an oval just to get it past some of the woodwork structure. The other challenge is that where I wanted the exhaust air was a long way from these panels. This is normally considered a bad idea because of potential heat loss. In fact, I could feel a little warmth on the exterior of the insulated ducting, so I later covered the exhaust ducting with a thick layer of insulation. So far, I'm happy with these AC Infinity Cloudline duct fans. I bought a couple of their 4-inch duct models with their simpler controllers. These things are designed to push air through ductwork that can be somewhat restrictive. Although these things are pretty quiet, as I increase the speed, they are a little slow to respond. You can see that they can generate a fair amount of noise. Because I decided I should also have filters on these things, I built these noise muffling filter boxes that I put on the intake side of the air heaters just before the blower motors to muffle the noise that I was hearing from the intake registers. Yes, I chose to push air through these heaters instead of pull air from them, largely because I felt that the heated air might shorten the life of these motors. The exhaust registers were very much noise muffled by the air heaters themselves. Down below, I have both air heaters exhausting into our open floor plan living room, dining, and kitchen area, but then have one of them split off to one of the bedrooms that needed some help. For air return, I was lucky enough to snake the ducting down this hollow wall to the floor. I wasn't so lucky with the other one, so it resides in a hallway ceiling. I won't be using those simple controllers, but instead wiring my own cables to the low voltage terminals of those motors.
Okay, here we have the little controller I built to control this thing. As you can see, we've got the other end of the motors, blower motors here. They are providing 10 volts to this unit that you will see in a minute that I'm summing them with a diode isolation to do load balancing between them and then converting it to a lower voltage. I've got the PWM control signal to control the speed of the motors, plus I've got feedback coming from them to give me the RPM. This wire mess here is all the temperature sensors, 5 of them that I've got wired into this thing, which I did completely wrong. It turns out the one wire bus wants to be daisy chained, not a star configuration like I'm doing here where I'm combining them all in together, which I did get standing wave problems with that I could measure on an oscilloscope. I minimized that by isolating them with little resistors here. It made it work. It's just not the right way to do it. This was a nice cardboard box, actually, that had a magnetic lid to it that I just didn't have the heart to throw out. But it opens up, and on the inside here, we see the voltage converter that takes the 10 volt, the sum of the 10 volts from the two units, then converts it down to 5 volts to feed it into a Raspberry Pi Pico 2-W, the W because it has Wi-Fi on it. And then these units here are drivers because the controller motor wants 0 to 10 volts PWM, but this thing can only produce 0 to 5, and so this makes that transition. This USB connection here is a temporary thing. It's going to this Raspberry Pi 0W that I use for software development. It's running Thonny, the Python IDE, that I then interface to the MicroPython interpreter that's on here that since the software is still under development, I go in and do some tweaks to it every now and then. This unit does not require this to operate. Eventually I'll unplug this when I consider the software done and let it run by itself. And that's because it really is powered from the motors themselves and not the USB.
Shown here is the software I've mostly written. You can see various aspects of both of the panels. It normally runs by itself, but if you notice, it knows what time it is, or more importantly, what time of the year it is, as in I may be adding some software to say, hey, don't run this in the summertime, no matter what. This web page has interface to a pre-existing weather station that I've had for the last 20 years that also gives me indoor and outdoor temperature. So normally this thing is in normal mode where it automatically does the right thing, turns the motor speed up and down as it computes that it needs to. But I can put it in manual mode and change the speeds all I want, turn them up or down. You'll see the RPM on this one start to drop, and then you can go back to normal mode. I've hardly ever had to use that. The other feature I have is right now, this software crashes every now and then, usually when I try to use it with a phone like this one. This turns on and off the LED inside the unit that I use as a quick marker to know that the hardware watchdog inside the Pico has rebooted the processor since the last time I turned the LED on.
So now to get to what you are all wondering, how well does this thing work anyway? Well, the short answer is it's a little underwhelming. For a longer answer, let's get to some data here. I have the Pico exporting temperature data to some software I have running on a 20-year-old Buffalo Link station that also imports data from an old LaCrosse WS2310 weather station, which has its own temperature sensors for indoor and outdoor temperatures. So all this data is combined on one graph and saved daily. The first graph is always the current day and is created on the fly when you request the web page. Note we have outdoor temperature, indoor temperature, and the temperature of each of the solar heaters. I also had an extra sensor that I simply put up in the attic just to see what's going on here. You see today we had a few clouds come in. So we started out with the thermostat on our gas furnace set at 57 degrees. Furnace turned on and warmed it up to 57 degrees. Then, when my wife got up shortly before 8 a.m., she turned the thermostat up to 68 degrees. The reason it seems like it took a long time to get there, I suspect, is that there is some extra thermal mass in the temperature sensor in the weather station that doesn't exist for the temperature sensor in the furnace thermostat that is mounted on the wall less than a foot away from it. So therefore, it takes a little longer for it to respond. So once it got up to 68 degrees, about at the same time the sun came out and quickly heated the box up to well over 100 degrees Fahrenheit, even despite the clouds. at which point it started heating the house. As you notice, it eventually heated the house up to almost 72 degrees, maybe 71 something, before it finally started falling back off again. The reason why there is a big gap between this sensor and that sensor is that with this one there is a little tree in the way that shades it. I've been slowly trimming some branches off that tree to try to extend this time a few minutes with some success. Perhaps we could harness a little bit of heat from our attic at certain periods of time on a different project that could be controlled by this same Pico. Just for grins, let's look at some other days here. There was a really cloudy day. Scrolling down here, another cloudy day. Okay, so here was a nice sunny day. If you can tell, wife turned up the thermostat on from the gas furnace when she got up early in the morning. Probably she only turned up to 66 degrees that day, which she does sometimes. And then it was a nice sunny day, so it reached 75 degrees inside the house that day before falling off. But it also was a pretty warm day outside here. Here is an example of a bad and cloudy day. First, this day was before I had the Pico's watchdog rebooting the Pico if it crashes, so we lost some data right here. Then notice that the heater temperature never got very high. In fact, I'll bet those blower motors never got any more than 1/3 speed. This graph would then show typically what happens in the absence of solar heaters. Notice that the gas furnace here cycles on and off about every half hour throughout the day, when normally the solar heaters would be providing heat during this time. It looks like we eventually got cold that day and turned the thermostat from 66 degrees up to 68 degrees before we turned it down at bedtime. Here is an even worse example of a bad day. Notice the solar panels never even got up to a temperature warmer than the indoor temperature. And there again, the furnace was turning on and off almost every half hour throughout the day. And once again, I think we got cold, turned the thermostat from 66 up to 68 degrees, and so it cycled up there for a while until we turned it back down to a lower temperature for bedtime. Here is another example of a good day. However, this was a day that we decided not to turn on the furnace at all. So all the heating you see here is mostly done from the solar air heaters themselves, but this was an abnormally warm day in the first place, so it worked very well and got the house up above 70 degrees, maybe 71 degrees, from 60 degrees all by itself, other than perhaps the house would have warmed up a little bit since it was a warm day outside as well. It is too early to determine the real cost and fuel savings from this data. In November, we used half the natural gas as we did the previous November. However, this year has been the warmest year and November in recorded history for this area, so that has to be considered. Should we return to more normal weather, the perceived effectiveness of these panels will likely decrease. Not including my labor, I have about $1,200 US invested in both of these panels together. Both motors together draw 60 watts of power when running at 100%, which is about 2% of the energy required to run a heat pump. Although I do expect this project to pay for itself in just a few short years, unless they suffer a disastrous failure, I would have liked these things to produce at least 50% more heat in the dead of winter. I do expect they will do a better job keeping our house at a comfortable temperature in the fall and spring months when the days are longer and the sun is stronger.
When I first got them running in early November, they did manage to heat the house to 78 degrees Fahrenheit one day without any help from the gas furnace. So this ends the part of the video that would be of interest to most of you. Next, I'm going to get in the weeds and geek out about the software I have running on the Pico. In summary, it is this. I'm running MicroPython on a Raspberry Pi Pico 2-W. The software adjusts the motor speeds using PWM waveforms to each of the blower motors, computed from a simple formula that basically subtracts the indoor temperature from the heater's temperature and computes a good speed that the motor should run at and updates it twice a minute. The software also exports a web page that establishes a WebSocket back to the Pico so that the Pico can send JavaScript object notation updates to various document object model ID tags on the page as the data changes. The software also opens a socket to my hacked Buffalo link station to get heater temperatures and then import them into some pre-existing software I have running on it that also graphs data from my La Crosse weather station. The software gets RPM data from the motors using custom programming of a couple of the state machines available on most of the I/O pins. It also implements a watchdog to reboot the microprocessor if the software crashes, which currently it does about every other day. So now for some full disclosure. I am very rusty at programming. In fact, my formal training was before object-oriented programming was even conceived. Therefore, I had lots of troubles wrapping my head around that concept, especially the hierarchy of all the object inheritance and how it affects the program flow. So jumping in head first to learn Python for the first time, a language where almost everything is an object of some sort, was quite a leap for me. Other things I have limited to no previous knowledge of that are used here are the Pico itself and its tricky state machines, JavaScript, HTML5, cascading style sheets, WebSockets, document object model, the MicroPython Pico implementation, and the Thonny integrated development environment. So a steep learning curve for me. To help out, I've stolen some sample code to do both the WebSockets and state machine pulse counters from others, thank you, and modified it for use in this code. Because of all this, I consider the code in this thing to be of low quality. At least I know enough about coding to realize that. And incomplete. At this time, there are details such as logging into my Wi-Fi that is hard-coded into the software instead of being on a separate configuration page that writes out the data, JSON, to the Pico's file system so it can be read back in upon software startup. Finally, I'm obviously not proud of this code, but you can download it here, hopefully to improve it.